So we've been doing these interviews. We'll keep doing them. They seem to be doing well. So this time we've got a new guest, another one of our partners from Ponos Technology. Wonderful guy, very, very smart guy who I admire very much, actually. So it's very nice to have you here, Zarko.
Thank you very much.
Yeah, maybe you could just tell us a little bit about yourself and introduce yourself to the Telos community.
Thanks, John. Hi, everyone. Thanks for the nice introduction. I'm Zarko Gvozdenovic from Ponos Technology, head of software there, and started some time ago cooperation on the Telos and Snarktor with Alberto and with John. Maybe something about my background. I started actually my professional career as a software engineer in the Netherlands. Back at the time, 2009, let's say it was a crypto public key infrastructure where we made cross-platform cryptography software. Then I switched my career and started in the chip lithography. It's ASML, nowadays really a world famous company for the chip lithography, for the smallest, let's say, footprint of the chips or the semiconductor distances, let's say at nanometers level. And then a while ago got introduced via a good friend of mine and now associated Ponos Technology, Vladimir Petrovic, to Ponos, and via Ponos then eventually to John and to Telos when we recently started working. At Ponos we are doing hardware accelerations that you may have already heard in the series of the previous interviews, and we try to really optimize it to the level of either throughput or price, and to keep that balance still capable in our accelerator. So whoever needs more throughput, we can go for that, we can tune for that, and whoever needs better price, let's say, that can be also achieved.
Yeah, so maybe we could dive into chip lithography a little bit here in a sec, but I'd like to kind of maybe talk a little bit more about you because I think you're really interesting. So you're kind of like a Dutch guy almost, right? You've been
almost the Dutch guy, yes.
Yeah, you've been in Holland for many years now.
15 years, to be precise, indeed.
And you know, there's kind of like this meme with these Eastern European guys. We share a Slavic heritage. They tend to be very technical, super smart. But I do think there's a next level to it in terms of sort of a type of self-awareness, mindfulness. It's almost like, to me, you have a much more holistic philosophy by your approach to life and just the way you think about things. And I'm just wondering if you can talk a little bit about, kind of your life experiences and how you got to this point. I think you're a very mindful person. I think you're a very self-aware person. Yeah. And even though you're like this like super smart technical kind of like Eastern European origin guy, but I think you've transcended a little bit, and I think your personality is very interesting. So
thanks a lot for having noticed that. That's exactly indeed how my self-perception also developed in the course of the years. Indeed, it started with a very hardcore, let's say, technical studies, electrotechnical university in Novi Sad, and software engineering specialization on that. And then, well, my first job was also very, let's say, what we could use in the software engineering terminology, very hardcore software technical cryptography and performances in bits and bytes and that stuff, you know, not to go into many details. However, where life brings you, right, it brings also challenges of the life, not just which are, well, per definition, not technical, they're non-binary in the sense of it's not black and white, but it's all the nuances in between. And that's exactly the trace that I followed both throughout my career and life, and it is what it was. It's been a challenge, it still is, of a constant adaptation, but not you losing your core values, your core self. Because that's, in my humble opinion, what the additional added personal value is to you, to your family, to people around you, and to your also business associates, and eventually the world, which we can all bring, let's say, through what we do and how we act and how we cooperate with each other. Oh. That's why once I recognized that, and throughout, let's say, especially the chip lithography journey of 9 years, because it's really, it is still a very big enterprise. That's where you also learn all the organizational, social, people, let's say, stuff, and you integrate it and you build up on top of the hardcore technical expertise, which makes me and people alike, let's say, a bit more, let's say, added value to all of us and to our dear ones, as I already mentioned. And that's how it actually brought me where I currently am.
Yeah, and also a lot easier to work with. because actually I say this all the time, like, you know, the ZK stuff and maybe the underlying components, and as you go deeper and deeper, whether it's on the software or hardware side, it's like hard. It's very, very hard.
Exactly.
And so you come up and face these like tremendously difficult challenges. And so the extent to which I think you have a good philosophy is really important, because, you know, you have to kind of like iterate through really difficult things. Exactly. And so I really appreciate that about you. It kind of made me think about, like, you know, you sort of look at post-World War II, we enter the computer age. There's basically some type of parity almost between, let's say, the United States and at that time the Soviet Union. I mean, they sent people to space first, right?
Yeah.
But then you go into the 60s, and the 60s, we kind of have this like hippie revolution. We get all these like smart people in California doing psychedelics. Yeah. Suddenly in the 70s and 80s, like the internet is proliferating and America's in front by a lot. And by the time we get to the 90s and the 2000s, it's very clear. And I think it comes down to, even though technically they started roughly, let's say, at parity, I think it comes down to culture and the way people sort of like approach life, the way they think about things, and then ultimately how that factors into solving really hard problems. Yeah. You know, the reason I mention it is just because obviously we both have an affinity for Serbia, for Belgrade, and this place seems to be transitioning, and I think this is kind of a little bit of a cultural transition.
It is.
And if they and really broadly throughout Eastern Europe, because there's just so much talent, but somehow it's locked into certain types of mindsets.
Exactly, and that's exactly what helped me. Thanks for bringing that up. Basically, the society in which we live and in which we create the value and in which we shape ourselves, and that society is what is like a circle, you could say it, which shapes us, and we bring the value back. What helped me tremendously is, for instance, the Dutch society, which is very, very, very modern, developed, adaptive, understandable, and thankful for integrating all the diversity and all the cultures, and that make me realize certain things which, at least in the times when I was young and then when I was finishing the studies, wasn't really the case back at Serbia, let's say, where I was. Nowadays, luckily, it's changing, and it's changing tremendously, and which makes it even better possible, and we are more compatible to work with each other. So we are witnessing the, let's say, the thinning of the boundaries, at least physical boundaries between people, and that makes us, via remote working and via this also technology, via the blockchain, cooperate in such a seamless way that we don't feel the distances. We feel less and less the cultural, the business differences, the values. As you mentioned, and I just like to also reflect on that one and connect, this is a really hard domain.
Yes.
And a hard domain, making a hard software system like SnarkTor and what we're trying to achieve there at all possible different aspects is even harder. Unless you're equipped to, in a proper, very critical but constructive way, not criticizing the ideas, but critically approaching the ideas and people around you, if you make those iterations of making mistakes, falling down and getting up really fast and still staying friends, between ourselves and between the community for which we create this whole value, that is what makes our journey pleasurable.
Yes.
Not just the goal, which necessarily is going to follow up.
I couldn't agree more, and I'm glad we got a chance to talk about it, because I really was hoping the Telos community get a sense of your personality. That's why I like you so much. Okay, so maybe we can switch gears and get into chip lithography. Obviously, it's a complicated subject, maybe an introductory concept for a lot of people that might be watching this video. So maybe you kind of take us through and talk a bit about chips and physics and some of that kind of stuff.
Yeah, sure. Let me then not give some, let's say, an overview through the journey that I had, that I experienced through ASML. Where I started is the most modern, let's say, what's called in the world is now world famous, the EUV, extreme ultraviolet technology, and I worked there in one of the function clusters as a function cluster architect, let's say, and I started as a developer, where we created control software for those machines, which of course needed to have had a very high uptime, because, well, every down of an hour in a serious fab where chips are printed continuously 24/7 costs a lot of money and causes the disturbances in the complete fabrication process. After that part, let's say, of the career, I switched to computational, let's say, lithography there. So it's a different set of machines at ASML. So I also had to diversify there and to switch my mind and to my domain knowledge a couple of times. And that's where basically the YieldStar system came into a picture and the software for it. And the YieldStar was measuring basically when you do a layering of a chips. Now we're going into the chips, how it's created, right? You have different layers and you have misalignments there and you have focus offsets and many different aspects, right? And all of that have to perfectly come together so that the utilization of a die, of a wafer, is optimal. That's a very long story from multiple aspects, let's say, explained. So basically the stack that I covered there is from a very low systems programming software level of controlling such a big machine like the EUV lithography machine, where back at the time there was a CO2 laser which was shooting on the droplets of a tin, and that's how the EUV light was created. Shooting basically, it was 40 or 50 kilohertz, so 50,000 times, right? And it was capable of even shooting in between the droplets, right? Because how the EUV, the extreme ultraviolet light, was created was by the means of first making a small sort of a pancake of that tin, and then actually creating the explosion of light.
I see.
And in the vessel inside there was a lot of, let's say, mirrors, very specific mirrors created just for that machine, unique in the world, which were basically gathering all the lights in a single beam, and that single beam was doing the illumination eventually. Let's say on the die. So that's a bit of a fascinating part let's say, of that story. As we moved and as I moved, let's say, transitioned to the YieldStar system, where the yield is measured, let's say, and we thought we have a very big and very fast and successful measurement tool. The software stack was also going higher up, let's say, going from C and C++, going to C# and the microservices and the orchestrations of that, which you can find also back in this industry where we are, right?
Yes.
Once we do the provers and the aggregators and the sequencers, those would be analogies to those microservices. They would be obviously connected and orchestrated together. But then there is also systems part of it. The closer the more you want to squeeze the performance out, the closer you get to the CPU performance. And once you can't go further than what the CPU assembly level instructions offers, right? What is in the most of the provers done nowadays to speed them up as much as possible via SIMD. Then you go to hardware accelerators like the ones we make, right?
Yes.
Now going a bit back and forth between chip, that's always how I try to make a bridge and make an analogies to explain it, especially to the audience who might not be so technical. What is the actual relation? Well, that's it, what I just mentioned. And that's what also empowered me to be able to think of complex systems like this using the analogies and making switches really quickly and effectively and efficiently so far.
Yeah. So I would say, for our viewers, this is, we talk about hardware, software, co-design.
Exactly.
And this is in some depth with some specificity, why that's important and to some extent or a large extent what that exactly means. So I always say it's not the case that you just sort of build some software, plug in a machine, and now your whole ZK thing is like running faster.
Exactly.
So I'm just wondering if you can kind of drill down even more, and specifically with respect to ZK, why hardware software co-design is so important, and in some detail kind of what that means with respect to, in particular, all these different components, right? We've got sequencers, schedulers, provers, etc. We have multiple actors in a highly complex system. Yeah, maybe you can kind of freestyle on that topic a bit.
Sure. I'll do that happily, and because there's so many actors, right? Yes. I will not go into all of them. Maybe in a kind of a different occasion, but I will just zoom bottoms up, let's say, from the perspective of the prover, because that's the actual part, let's say, that we have successful and that we are successfully speeding up and optimizing. Why is software hardware co-design there actually essential? Many times when you want to have something really you want to squeeze the last juices of the computational unit that you have at your hand, you need to look at the architecture of it, hardware architecture, let's say, of a CPU, in terms of its behavior, how it's meant to crunch the data, how it means to crunch the instructions, what are cache misses, and how to avoid them. And when we talk about instructions, we should think of words, of a number of bits, 32, 64 bits, and that connects nicely to the cryptographic fields of the cryptographic systems that are used, right? And when you develop such a system and when you want to speed it up, you look from the perspective of the hardware unit that's going to do the crunching, multiplications and additions mostly, and you want to optimize for that. If you want to optimize for that, that means that your data structures, not so much the algorithms, but the data structures primarily are optimized for the pipelining and the streaming of the data as fast as possible through the pipeline of modern CPUs.
Yes.
When you go to different sort of accelerators, you have a different architecture, you have different data formats, and you have to implement the same algorithms to achieve the same, let's say, functional intention of the original system. And to put it very simply, that means the same cache, right? If you're doing cache calculations. And that's very easy also to say and to test once you close the complete circle and once you close the complete chain. It's very hard to achieve unless that shift of a paradigm is taken into account from scratch, from the beginning. And that means if anybody wants to really develop or to adapt a certain proving system to its optimal potential, that needs to be taken into account either early on or a certain serious re-architecture needs to take place so that it's adapted from the perspective of the data structures and specific maybe algorithmic adaptations which make certain hardware accelerator shine more than a CPU in a certain segment.
Yeah. So I guess one of the ways I talk about that is ZK proving is going towards ASICs, but there's an FPGA interim step.
Exactly.
Right? And so maybe you can drill a little bit into exactly what that means, kind of the difference between FPGA and ASICs, and why that interim step is likely to sort of be the case before we get to a more final state with ASICs.
Yeah. So let's then start from the perspective, what is the challenge with an ASIC? If you're completely sure what kind of an algorithm you need to implement on the chip, on the new chip that needs to be designed and completely produced, then you're done. Then you don't need these intermediate steps, basically. There is another challenge. Maybe you're sure for a specific algorithm what you want to develop a chip for, but there might be other algorithms that also need the acceleration and that you may need a specific different chip for, which again goes into the same challenge of having chip fabrication, which is a costly process which takes very long. It has a couple of iterations, and every iteration costs tens of millions of euros, of dollars basically. Because of that, you have an intermediate, kind of a sweet spot, kind of a playground. Me as a software guy, I'd like to see it, let's say, like that, an FPGA in between, or GPU for that matter, but we are specific in FPGAs. How so? Well, there with a much smaller or much shorter development cycle, much less resources and money, you have a reprogrammable, hardware capable by nature of its hardware design, parallelizable device, which uses really small clock frequency compared to modern CPUs, therefore small wattage, therefore saves the electricity.
Yes.
Well, which is the essence, which is the fuel, right, of doing continuously those cryptographic calculations. And this is what's the connection and what's the path, actually, the journey to a successful ASIC development. So one could say, once we are sure about our proving systems in any given product, and once we are sure about the set of algorithms that we actually want to have ultimately optimized, it's a very, very good way and advisable way to go the route that we took, to go via the FPGAs for the reasons that I just mentioned, to actually exercise the ideas, make successful accelerators, which are just on their own also good enough for certain applications as use cases. So one could say I don't even have to go eventually, let's say, to an ASIC design, but there is still open door, as we like in the hardware and software architecture to say, you don't want to close the doors, you always want to leave the opportunities, but have something really modular and extensible, now developed and ready for the future.
Yeah, that's sort of like a brilliant, detailed explanation of these memes that I'm trying to introduce, which is sort of like in the case of Telos, I talk about it all the time. We're taking a very flexible approach. You look at many of these other projects, and like I've always said, I respect all of these people. They're my heroes. These researchers are tremendous. However, at the same time, there's enormous amounts of investment, and so there's like, let's say, many interests, helping shape strategy. Then there are some hard or very strong assumptions, whether that's about a prover or, I don't know, some certain type of approach. And now you're off to the races. And suddenly these things get big. And it's kind of like, well, what you have is like a very large aircraft that's in mid-flight.
Exactly.
And if you need to re-engineer that aircraft in mid-flight, it's very hard, right? That's like kind of impossible almost. At the same time, however, the entire ZK ecosystem continues to innovate, right?
Exactly.
The cadence and pace of innovation is incredible. It's increasing. So each month, each week, I don't know, almost every other day, there's something new.
Exactly.
So the approach, I think, and I guess we all share a similar view, is be agile, be flexible, fail fast, fail cheap.
Exactly.
And then in one moment, the components and the pieces will be mature enough that you can put the pieces of the puzzle together.
Absolutely,
Yeah.
absolutely. Fail fast, fail cheap, and fail predictably.
Yes, yes.
Or as predictably as possible, right?
Yes.
And that's exactly what we just described in this conversation enables us to be really sure in ourselves that we know what we are doing. And I hope that I managed to explain that and to convince, let's say, the viewers, let's say, of what we're talking here about and what we are building for the community and for all of us, for the world, that this is the right way because it enables us to basically act quickly, to adapt as we need to adapt, and to have really fast development cycles.
Yes.
With very concrete results, like the results that we just, with our, let's say, first POC, demonstrated really successfully, and people are here really at ETC in Brussels, very satisfied about that and showing very much interest. So we're definitely gonna set it forth, set good next steps, and keep the community updated with what we are actually doing, so that we also can get a certain critical reflection by the community. Is it only us who are actually convinced in our brilliant ideas, or there's many of us, let's say, together working and we're really critical, or are we actually successfully convincing everybody or the large majority of potential users that this is the actual right way and that we are on the right path to the success?
Yeah, so let me just ask you one more kind of last question here. It's a little bit of a spicy question, but I often talk about if we move in this direction of ASICs, then it introduces the potential idea for useful proof of work, which Alberto has talked about in the past, could even be something like a hybrid consensus with useful proof of work, proof of stake. I'm just wondering, like, do you have any thoughts on that? And what do you think?
Yeah, that's a very challenging question indeed. I would be, let's say, hypothesizing at this point about how the future would look like, but definitely I can share, let's say, your standpoint that you just mentioned, that it creates a very big, let's say, opportunity for the useful proof of work. And at the same time, we are in front of a big challenge that we just touched. And as with every challenge and with every great success, it can have, let's say, two sides of a medal at least. And let's see, let's keep, let's say, the community a bit also excited and curious about that. What's that going to bring for all of us? But hey, as we are going through this together, we are making it and we are witnessing, we are basically creating day by day our reality, and from tomorrow's perspective, let's say, a bit of a history. So let's see where that brings us.
Yeah.
Anyway, I definitely see this as a really exciting journey, really challenging one with a lot of smart people, and I like the challenge and I like how we really collaborate with one another. Let's keep up the good work, I would say, and really thanks here for having me.
Oh, very good.
On this talk.
Very good. No, thank you. And yeah, let's keep talking. And I guess you're also on Twitter, is that right?
Yes, I am.
Okay,
Yeah.
so we'll put your username on the screen. And yeah, thank you very much. Super cool. Outstanding.
You're welcome. Thanks, guys.
Very good, very good.